Ripping and rolling here in Chapter 8. As a heads up to you guys, Chapter 8 tends to be one of the more difficult chapters that we do this semester. As I was saying here at the beginning, the front half of Chapter 8, the things that you're doing, like the calculations and things, are all relatively simple. The hard part is like keeping track of the vocab and the notation and all of that. Things get much more complicated in the second half, in the back half of Chapter 8. That's where the difficult things kind of come in, and it even more so if you don't have the notation, the vocabulary straight from the first half. So just as a heads up, if you have an A game, you may, you'll want to be on point here in Chapter 8 because it's a lot of vocab, a lot of notation, and then things start getting complicated in the back half of the chapter, calculation-wise, on top of that. So really try to stay on top of things. Don't let the homework sit in forever. Make sure you're attentive and kind of zoned in and all that kind of stuff, okay? Cool. So all of Chapter 8 is talking about vectors. We're going to start Chapter 8 talking about vectors of the two-dimensional variety. Now, some of you know a little bit about vectors. Some of you might know quite a bit about vectors, and some of us probably know next to nothing about vectors. That's okay. We're going to start as if you are in the next to nothing camp. So we'll just kind of start by defining some pieces. So we say that a two-dimensional vector is just a pair of real numbers that represent two quantities, magnitude and direction. So the notation we use to describe a vector, when I'm writing it on a sheet of paper, I put a little hat on top of my vector. That hat is like a half arrow. If you're typing, again, you could use the half arrow if you're typing. In the lessons, we use boldface. Again, easy to make boldface when you're typing, hard to make boldface when you're writing. So, okay. So that's the notation that we'll use for a vector when we're writing on paper and probably on your worksheets or in the lessons and the homeworks. We're using boldface to represent a vector. So the first part of what we're doing here today is going to be talking about these different representations or different ways we can represent a vector, and then kind of converting back and forth between these different representations. So the first one is like a geometric representation. So if I draw like a graph, my vector on that xy axis consists of 2 points. The point where the vector starts, called the tail. And the point where the vector ends is called the head. At the head, typically draw with the arrowhead there to represent a direction. So when we look at a vector geometrically, the length is the magnitude. And if we imagine like at the tail there, in a little imaginary xy axis, our standard form angle then would be the direction. But really, when we talk about a geometric representation of vector, we're just talking about it 2 points, right? A point for the head and a point for the tail. Okay. Our second representation is just, if we just give you the magnitude and direction. So for example, I think in first semester we talked about like, oh, if a plane's flying at 250 miles per hour at a bearing of, I don't know, 105 degrees or whatever, that is information could represent a vector, and that the speed is equivalent to the magnitude and the bearing equivalent to the direction. So again, you could just say like a vector with magnitude 8 and a direction of 56 degrees or something, like you could just state it. And the last one is component form. And when we talk about component form in this class, we're going to be talking about like the standard representation of component form. So if we write our vector in component form AB, notice that those are wedged brackets. They have like a point to them. They're not parentheses. They're not curly brackets. They're like these wedged brackets. What that's saying is the tail of our vector always at 0, 0, and the head of our vector then at the point AB. So when we talk about something in component form, that's what we really mean is a vector whose tail is at the origin and whose head is at that same point as that vector. So we have 3 different representations, and we'll use all 3 of them to do various things. And it's important to be able to convert back and forth between them, because some things it's easier to do in component form, and some things might be nice to have in geometric form or as a magnitude and direction. So going and being able to kind of convert back and forth is going to be helpful. So the first conversion we'll talk about is going from geometric to component form. So again, in geometric form, we have 2 points, one at the head and one at the tail. In component form, basically what we want to do is we want to pick up that vector and move it so that it's the same length and still has the same direction, but the tail of the vector has been moved or translated, if you want to use the geometric term, so that it's at the origin. Well, very simple to do that. All you're going to do is take the x coordinates and do head minus tail, and the y coordinates and do head minus tail. Sometimes we call this the head minus tail rule. I abbreviated head minus tail as HMT because there's a lot of letters. Cool with that? Again, very, very easy calculation to do. Nothing complicated, but requires to remember like what all these things mean, right? Next thing we're going to do is talk about going from component form to a magnitude and direction. So if we have the component form AB, really that's a vector whose tail is at the origin and whose head is at the point AB. We know that the magnitude is related to the length of the vector. So if you want to find the length of a segment geometrically, what tool would we use? The distance formula, right? If you remember back from geometry, the distance formula is d is equal to the square root of x1 minus x2 squared plus y1 minus y2 squared. So in our case, let's do that for a moment. I'll get back to the vertical bars here in a second. So since one point is AB and the other point is the origin, when I plug that into the distance formula, I just get that. And since in component form, the tail is always at the origin, our other point is always 0, 0. So that just simplifies down into the square root of a squared plus b squared. Now notice the vertical bars here I'm using as my notation for magnitude. And at this point you'd be like, yo, Mr. K, you're abusing the heck out of this vertical bars notation because now this is a third operation that I've had since I've started high school that uses these vertical bars. And I'd go, yeah, you're right. So remember in your algebra class, vertical bars around a number is representing the absolute value. In your Algebra 2 class, the vertical bars around a matrix is representing a determinant. And in this course now, the vertical bars around a vector is representing a magnitude. So it's very important that you're understanding the notation and you're looking at what are these vertical bars surrounding. Is this a vector? Is this a number? Or is it a matrix? Because that is going to tell you what those vertical bars mean. Because the vertical bars by themselves could be any one of those three things, right? So it really matters what is inside the vertical bars. That's how you can tell if we're talking about a magnitude, a determinant, or an absolute value. Since there is no such thing as the absolute value of a vector or the absolute value of a matrix, and there's no such thing as the determinant of a vector or the determinant of a number, and there's no such thing as the magnitude of a matrix or the magnitude of a number. It's all unique. So what you're taking, what's inside the vertical bars really tells you what's going on. Everybody's cool? Okay. The next piece then is we need the direction. So, okay, let's say that we have our vector then. We'll draw a little picture here. Here's the point AB. And our direction then, we're just going to use the standard form angle here, theta. And now this looks exactly like a first semester problem. So I'm going to do this the exact same way. I'm going to call the angle between my vector and the x-axis alpha. And I'm going to observe that the other arm of alpha is the 180-degree end of the y-axis. So I can say then theta is equal to that other arm of alpha. And since the last axis we crossed through was horizontal, it's going to be subtracting. And then I know alpha is just the tan inverse of the absolute value of, in this case, y over x. So b over a. Just like we did in first semester, exactly the same idea. So again, remember that the number that we're subtracting alpha from comes from the other end of the x-axis that makes up alpha. And that whether we're adding or subtracting alpha is related to the last axis that our angle theta passes through. If it's a vertical axis, it's subtraction. If it's a horizontal axis, it's addition. The nice thing about the directions for vectors is there's no reason that you'd ever use a negative angle. There's no reason you'd ever use an angle that's bigger than 360 degrees. So it makes these calculations pretty easy since there's never reverse things going on. There's never coterminals that you have to worry about. It's always just between 0 and 360. Cool? Okay. And then we need to do magnitude and direction to component form. So let's say we have some vector v, where we'll just write its magnitude as the magnitude of v. And I'm going to use theta to represent the direction of vector v. Okay. So the component form is just going to be the the magnitude of v times cosine theta, and then the magnitude of v times sine theta. Does that look familiar? First semester when we did the navigation problems, we resolved our vectors into horizontal and vertical pieces and then added and subtracted those horizontal and vertical pieces. The way we resolved them into horizontal and vertical pieces was exactly this, right? So again, just borrowing something we've done from first semester to use in a different context. That's pretty cool. I'm happy whenever we have a chance to do that. Anytime I can use a routine that I already know, I'm good with that, right? Okay, so this is it. This is all we need. Notice that I'm not going to do a geometric to component form. A geometric to a magnitude and direction. Why not? Well, because I would just go geometric to component and then component to magnitude and direction. That's actually the easiest way to do it rather than going directly. Everybody cool with that? And the other piece that I'm missing is component to geometric. That's trivial though, because the definition of component form is the tail at 0, 0 and the head at the component. So there's nothing really to write there either. Everybody cool? All right, let's take a pause here and do a couple of numeric examples before we get going any further. So let's say that for the vector xy, where x is the point 3, -2, and y is the point 5, 1, we want to put that into component form. Since we're going from a geometric form, 2 points, to component form, we're going to be using that head minus tail rule. Which vector or which point is my head and which is my tail? Luke?
Y is your head.
Yep, and x is your tail. How can you tell that? Yeah, so Luke's looking at the vector notation here. So that's telling us that the x is the tail because the tail of our arrow is over the x, and y is the head because the head of the arrow is over the y. So head minus tail, head minus tail, and I get the vector 2, 3. One line calculation. Similar thing, you'll do some similar things in your homework, but very easy, right? The tricky part is just remembering how to do it, like what the names mean. But the actual calculation itself, really, really easy. Next example. So let's say we take the vector 2, 5 and want to convert that to a magnitude and direction. Actually, let's make that negative 2, 5, excuse me. Let's do that. So the magnitude is really easy. Negative 2 squared plus 5 squared, all square rooted. That gives me the square root of 29. Now, if that was a radical that I could reduce, I'd probably reduce it here. Or depending on the context of the question, even convert that into a decimal and round to like 2 decimal places or something. Would depend on the directions. For right now, I'm just going to leave it as the square root of 29 for this example. Everybody's cool? Okay. The direction then, go ahead and plot the point negative 2, 5 to draw my vector. Then I'm going to be looking for this angle for the direction. So I'll draw my alpha. The other arm of my alpha is this 180. So theta is just going to be 180 minus alpha, where alpha is the tan inverse of the absolute value of b over a. So I'll just go ahead to my calculator, 180 minus tan inverse. And I'm going to do the absolute value in my head just so I don't have to go through all the buttons to press to get that in there. So I get 111.8. Okay. And then let's say that we have a vector whose magnitude is 5 and its direction is 224. And I want to take that to component form. Just as an aside, sometimes we call this resolving the vector. Where we go from a magnitude and direction into a component form. But very easy to do it. So when I type this into my calculator, I get negative 3.60 and negative 3.47. Again, like basically one line of computation, right? No big deal. So overall, of these 3 representations that we have so far, we'll get a 4th one a little bit later. The 2 that are the most useful to us in a practical standpoint are the component form and the magnitude and direction. The advantage of the magnitude and direction is that often those have real-world meanings to us, as we saw in the navigation problems that we did in first semester, where the magnitude was representative of the speed of your thing, and the direction was representative of a bearing, like actually where you need to point your ship to go. That's nice. The component form, the advantage is that the actual calculations that you're going to do are much, much easier using component form. So the usual pattern for a lot of these vector problems is you convert everything to component form, do your calculations, get to your final vector, and then take that back out to a magnitude and direction, where we do most of our work in component form and then report our answers in magnitude and direction. Is kind of the usual. So that being said, our next section, we're going to talk about vector operations. And all of our vector operations we're going to describe in terms of vectors in component form, because that's going to be our usual workhorse representation. Most of the things that we're going to be doing in this class, we're going to do as vectors in component form and then kind of report them out in whatever form is as directed, but the work will be done in component form by and large. We're going to start by defining a very special vector called the zero vector. Yes, sir. What's up? Oh, okay. So the zero vector, I'm going to name with a special letter. What letter do you suppose we're going to use to name the zero vector? O. Yeah, why O? Looks like a 0. So the zero vector is equal to the component form 0, 0. Keep in mind that I'm putting a hat on top of my zero vector. You should get in the habit of doing that. It's very easy to confuse the zero vector with the number 0, which are two very different things. Keep in mind in the text, we're using boldfaces for vectors. So like a boldface 0, sometimes it's easy to confuse that with the number 0, just as a heads up. So that's a vector with magnitude 0. And no direction. Which I guess at first glance, that seems kind of odd. The zero vector is the only vector that doesn't get a direction. But that's not really uncommon with like 0 things. In the real number system, the number 0 doesn't have a multiplicative inverse, right? Like every other number has a multiplicative inverse, like 2 has 1/2. But you can't make the reciprocal of 0. So zeros are weird. So first thing we're going to do is define addition and subtraction for a vector. So if I have a vector, 2 vectors, I guess we should do that. So let's say I have my vector u, which is u1, u2, and my vector v, which is v1, v2. If I want to add v and u, I'm just going to add them component-wise, which is really nice. That's exactly the way we'd want it to work, where just we add the first components, we add the second components, and that's it. Graphically, what's going on here? So let's say we have the vector u is this, and maybe the vector v is that. If we draw u plus v, we're drawing u, and then where u ends, we're going to draw v. And then our vector u plus v then would be that. Is everybody okay with that? So if we look at those two definitions, the geometric and the algebraic definitions of vector addition, is vector addition commutative? Is u plus v the same as v plus u? Yes, right? Clearly, if I flip the order, u1 plus v1 is the same as v1 plus u1, since u1 and v1 are just real numbers. And then similarly, if I drew the picture, if I drew v first and then drew u, I end up at the same spot, right? So it still results in the same u plus v. Now, obviously, we get two different triangles, but if I drew both triangles at the same time, what shape do you see there? Parallelogram is the one you're searching for, yeah. But we know the diagonal of a parallelogram are congruent, so no big deal. And then similarly, vector subtraction is going to work exactly the same way, where we just can subtract the vectors component-wise. No big deal. So the first two operations we've done, addition and subtraction, you'd suspect the next two operations would be multiplication and division. Well, you're wrong. There is no such thing as vector multiplication or vector division. You cannot multiply two vectors together, divide two vectors. But we do have a type of multiplication that's defined for vectors called scalar multiplication. So if we have some vector v1, v2, and some real number k, I can multiply that real number k to a vector by just multiplying each component by k. Notice that k doesn't have a hat on top of it because k is just a real number, not a vector. V has the hat on top of it because v is a vector, but not a real number. If we draw a picture, yeah. Yeah. If we draw a picture, say, what does like 4v look like? So if this is v, 4v just looks like 4v stacked, head to tail. Everybody's okay with that? So that being said, it should feel pretty obvious that the magnitude of kv would be the same thing as k times the magnitude of v. Right? The length of 4v should be the same as 4 times the length of v. Everybody agree with that? From our picture, that should feel pretty obvious as a result. And that's a nice thing to kind of keep in mind. It can sometimes make magnitude calculations a little bit more straightforward. Okay. The next thing we're going to talk about is another type of special vector called the unit vector. So we say that u is a unit vector if and only if its magnitude is 1. So how many unit vectors are there then? You already know the answer to this. You just don't know you know the answer. How many unit vectors do you suppose we have here? Lily. Infinite is the correct answer. Well, okay, what do those unit vectors then look like? Well, every unit vector is in the form cosine theta, comma sine theta. Remember, on the unit circle, every point on the unit circle can be represented as cosine theta, sine theta. Every point on that unit circle is 1 unit from the origin. So the component form, tail at the origin, head at the point, cosine theta, sine theta, has a magnitude of 1 because the vector is 1 unit long. And since there's infinitely many points on the unit circle, there's infinitely many unit vectors. The unit vectors will be particularly useful to us because they capture the direction of a vector without actually capturing really any length, because the length is just 1 unit. So you can take like the direction of a vector and then scale it using a unit vector to however big you want it to be after. Which will come in handy in the future. So let's talk about that idea. So say I want a unit vector in the same direction as some vector v. Well, so let's say our vector v is just v1, v2. If I take the magnitude of v and then multiply vector v by the reciprocal of its magnitude, that's going to give me my unit vector in the same direction as v. Well, how do I know that is actually a unit vector? Well, if I take the magnitude of u, that's the same thing as the magnitude of 1 over the magnitude of v times vector v, right? Now, 1 over the magnitude of vector v is just a scalar. So I can pull that out of my magnitude, right? Like we just showed you guys a second ago. And 1 over the magnitude of v times the magnitude of v is just 1. Cool. And since the magnitude of v has to be a positive number, the scalar multiplication can't change the direction of v, right? Because we're just talking about like lengthening or shortening that vector. So you're good. So a unit vector in the same direction has to be. Let's just do a quick numeric example here. So let's say we just want to find a unit vector in the same direction as 5, negative 6. Oh, I'm just going to start by calculating the magnitude of v. So 25 plus 36 is 61. So here I'm not going to, again, I would reduce this radical if I could. Square root 61 doesn't reduce. I wouldn't convert this into a decimal in this problem. So my vector u then is 1 over the square root of 61 times the vector 5, negative 6. So when I do that scalar multiplication, I get 5 over the square root of 61, negative 6 over the square root of 61. And then I would probably rationalize my denominator here. So I'll call that 5 square root 61 over 61, negative 6 square root 61 over 61. But done in one line, right? No big deal. If you really wanted to, you could always check this by just calculating the magnitude of that vector we just found. What should the magnitude be when we do this calculation? Should be 1, right? So I'm just taking my answer that I found, and calculating its magnitude using the magnitude formula. Just to demonstrate to you that it is easy to check this. It just, again, one line on your calculator. And it comes out to be 1. So I'm quite convinced that it's done correctly. So far, so good? God bless you. Okay. So we have these unit vectors in general. There's 2 specific unit vectors that are particularly important. There'll be a third a little bit later. So we have these standard unit vectors. That we're going to call I and j. I is the vector 1, 0. J is the vector 0, 1. Now, these 2 unit vectors are important because they give rise to a new representation for a vector called the linear combination form. So if I have a vector in component form, say the vector CG, to write this in linear combination form, I want to write it as a constant or a scalar times I plus some scalar times j. Well, to do that, CD, or the vector CD, could be the vector C0 plus the vector 0D. Everybody good with that? That seems pretty obvious. And the vector C0 could just be C times the vector 1, 0. And the vector 0D could be D times the vector 0, 1. Everybody cool with that? Seems pretty obvious. And then the vector 1, 0, that's just the vector I. And the vector 0, 1 is just that vector j. So that's our linear combination form. Again, it's the vectors written in terms of a constant times I plus a constant times j. And really, it's really easy, right? The x component is your coefficient on I, and your y component is your coefficient on j. It's nothing more to it than that. Next up, we're going to define a new operation called the dot product. So if I have a vector u, that's u1, u2, and a vector v, that's v1, v2, we say the dot product of them, which we'll represent as u dot v, is going to be u1 times v1 plus u2 times v2. What do you notice that's kind of odd about this dot product definition? The dot product of 2 vectors is giving us a scalar, right? That is a real number. So the dot product of 2 vectors just gives us a number back. Not a vector, just some real number, like 7 or 2.5. Okay, sure. We'll do a couple of numeric examples here in a moment, but before we do that, I want to talk about a couple of properties of dot products. So the first is dot products are commutative. By that I mean that u dot v is equal to v dot u. There's a multiplicative identity property. By that I mean that the 0 vector dot any vector is just equal to 0. Notice again, the dot product of two vectors is equal to a number. So the 0 vector dot any vector is equal to the number 0, not the 0 vector, the number 0. There's a distributive property. By that we mean that u plus v dot w is u dot w plus v dot w. Or if you did the w in front, we'd say that w dot u plus w dot v. There's an associative property for scalar multiplication. So we're going to call that the scalar associative property. By that I mean that a scalar times a dot product, you can multiply that scalar into the first vector and then take the dot product. Or you could multiply that scalar into the second vector and do the dot product. Or you could do the dot product of the two and then multiply the scalar in. It doesn't really matter where you do that scalar multiplication, but it happens to just one of the things, right? And the last one is the magnitude property. And that just says that the dot product of two vectors is equal to the magnitude of that vector squared. We're not going to prove any of these properties right now. That actually lands in the homework at some point, asking you to prove these things. None of them are terribly difficult proofs. In fact, some of them are almost trivially easy, like the multiplicative identity one. You can probably see how to do that immediately. There's not much to it. Let's do some numeric examples now. Let's say u is the vector 2, 3. V is the vector -1, 5. And W is the vector in linear combination form 8i plus 4j. And we're going to do u dot v, and then w dot v, and then 5w dot u, and then u minus w dot, let's do dot 2v. Just do a couple examples here right quick. So u dot v, well, that's going to be u1 times v1 plus u2 times v2 u dot v, or w dot v, what's the problem there? They're in different forms, right? The u, or the w and the v. What am I going to do? I'm just going to convert w to a component form. So just 8, 4, right? The coefficient on the I is your X component. The coefficient on the J is your Y component. Okay, well that's easy enough then. So we have W1 times V1 plus W2 times V2 oh my goodness, not 16, that's an 8. So I get 12. For C, I have 5 and then times the dot product of U and or W and U. The way I'm going to do it is I'm going to do this as my scalar multiplication choice. So I'm going to do 5 times the dot product. So I have W1 times U1 plus W2 times U2. So 16 plus 12 is 28. And then 5 times 28 is 140. So far, so good. The last one here, I'm going to do U minus W, and then I'm going to do 2 times V, and then I'm going to get that answer and do the dot product. So U minus W is going to be 2 minus 8, so that's negative 6. And then it's going to be 3 minus 4, so that's negative 1. And then 2V is negative 2, 10. And then if I do the dot product, negative 6 times 2 plus negative 1 times 10 is 12 minus 10, or 2. Again, the calculation's pretty easy, right? They're just using formulas, multiplying and adding, and not terribly complicated, but you got to keep track of like what these different definitions are for the operations, so you're doing things the correct way. But the actual calculation themselves are pretty easy, pretty fast, right? Okay. Kind of 2 more ideas here. So the next thing we're going to talk about is the angle between 2 vectors. So let's say I have some vector here, U, and some other vector here, V. When we're talking about the angle between 2 vectors, we're talking about that. Everybody feel good there as to what that means? So to do that, okay, a couple of things here. So 1 This can be kind of a confusing formula. So here in the formula, this piece that I've highlighted, what operation is that? That one is a dot product because it's between two vectors. What is that symbol that I've highlighted in green? That's multiplication because it's between two real numbers. Remember, the magnitude of a vector is just a number. So even though both of them have the same symbol, we know that that symbol means something different when it's between vectors and between numbers, right? So don't be confused on that. The second thing to keep in mind is because our formula has a cosine inverse in it, we know that the cosine inverse's range is between 0 and 180. So the formula we've given here is always going to find the smaller angle between the two vectors. So it'll never find you the one that's bigger than 180. It'll always find the smaller one, the one smaller than 180. So not that it matters for the most part, because again, you're going to be just probably plugging things into the formula, not thinking about it. But if you drew a picture trying to look for intuition and went, wait a minute, why am I not getting an answer that's bigger than 180 when my angle in my picture is clearly bigger than 180? It's because it's giving you this one. Okay, so it's not always from the first vector to the second vector. It's going to be the smallest angle between the two vectors. Again, I don't suspect that'll be an issue, but I've definitely, over the years of doing this class, had students come up to me and be like, I'm not getting the right answer. Look at the picture. It doesn't make sense. And it's like, and you have to re-explain that. We're not going to prove the formulas that we just wrote here. They're basically just the law of cosines rearranged. So I'm going to skip that. The proof is in the lesson notes, though, if you wanted to look at it. But let's do a numeric example. I guess we'll give these guys names. Okay, so let's find the angle between the vectors v and u. So to do that, I need three things. I need the dot product between the two. That's 2. I need the magnitude. Let's see what's, oh, bless you, 49 plus 36, that's 85. Now in this problem, I'm not going to bother to reduce these radicals, even though I might be able to, because all I'm doing is plugging them into a formula, the cosine inverse formula, so it doesn't even matter that the radicals are reduced or not. I'm just going to save myself the hassle. So I just, on the top, I have v dot u, and the bottom I have magnitude v times magnitude u. And just calculator time at this point, my dudes. And I get about 85.6 degrees. Again, pretty easy, right? Like, not complicated. The complicated part, again, is just kind of remembering the dot product and the magnitude and keeping all the formulas straight and all of that. But the actual calculation itself there is not too easy, or not too difficult. This leads us to one final definition. We say that the vectors u and v are orthogonal if and only if the dot product of u and v is equal to 0. When we say orthogonal, what we're really talking about is that the angle between them is 90 degrees. So essentially they're perpendicular. But perpendicular is a definition for lines and segments and stuff, and not angles, or not vectors. So it gets its own special word, but still basically the same thing. So for example, if we wanted to show that, say, the vector -5, 8 and the vector 16, 10 are orthogonal, all we're going to do is do the dot product of the two vectors. And show that we get 0. Just one line. Pretty easy. Alternatively, what else could you have done here? You could have used the angle between two vectors formula and show that theta is 90 degrees. But shoot, that's a lot more work than this. At this point, I think I'm done. I think I pounded enough stuff through here. You guys should be able to handle 1 through 40 from the problem set. Again, it's a lot of numbers, but like everything we did in here was like 30 seconds for a problem. Like they're not long, they're not tedious. They're pretty quick. You just got to get used to using, the notation, using the operations. I know it looks like a lot. It's like 40 problems. And they do pile up quick because we're going to be doing a lot of stuff. But these problems are pretty easy to do. So like I would get them done and not let this stuff pile up, because we got a lot of stuff to do next week, and it's going to get, that next problem set's going to get real bad looking real quick if you start off your week like 40 problems in the hole or whatever. So yeah, I mean, I guess that's where I'm at. Reminder again, Sunday's problem set is just chapter 7, or chapter 7 review, excuse me. And the following week, we're going to be doing chapter 8 stuff. And it's going to be that problem set's going to end up being a big one, I think. And probably the one following that also will end up being a big one, depending on how much we're able to get through next week. But I think there's like 120 problems in this set, and then there's a worksheet. So again, stuff in the beginning, pretty easy. Some of the stuff even later on, pretty easy. There's some pieces at the very end that are like pretty time consuming. But the point here early on especially is to just make sure you really have the notation down and really have the definitions down. Like, how do you do these new vector operations? Shouldn't be something that by the end of the problem set you're still having to look up. Like, you really want to have these things committed so that it's fast, that you can find a magnitude really quickly, or you can do a dot product really fast, or you can do a scalar multiplication really fast, or a combination of these things, that you can convert back and forth between the forms. These all be things that, like, if you're able to get this down and get the notation down and the names of everything down and the definitions and pay good dividend as we roll into the next sections where things get start getting a bit more complicated. But I'm going to stop now.